purpose of our experiment is to test the performance of paper towels as an insulator. By testing with different quantities of paper towels, we aim to draw conclusions on how the amount of layers, or thickness of the insulator, correlates to the effectiveness of said insulator. To effectively perform this experiment, there are only 5 things that you need. The materials you need are 4 cans of your favorite drink, a thermometer, preferably one that's digital, an insulator of choice, in this case is 1 roll of paper towel, a timer, and something to keep the paper towel in place. This could be tape, a rubber band, or anything else you may use.
The procedure for this experiment was to first cool the cans overnight in a refrigerator and take them out once you are ready to perform the experiment. Second, surround each can with a different layer thickness of paper towel or the insulator of choice. Third, measure and record the starting temperature of each can. Fourth, start a timer for 60 minutes and measure and record the temperature of each can every 10 minutes. It's important to make sure that you wipe off the thermometer after every measurement. Last, analyze the data using an Excel spreadsheet or your choice of data visualization tool.
Start by opening all the cans. Next, take the starting temperature for all the cans. Wrap each can with its assigned amount of insulator and secure it with the tape, string, or in this case, pre-wrap. This is what all the cans should look like. Every 10 minutes, take the temperature of each can and record it in the Excel spreadsheet. Be sure to wipe off the thermometer after every can.
The results of this experiment can be seen in the graphs on the screen. Cans 1, 2, 3, and 4 started at relatively similar temperatures of between 54 degrees Fahrenheit and 51 degrees Fahrenheit. After 60 minutes, the temperature of can 1 had increased to 64.9 degrees Fahrenheit, can 2 increased to 62.1 degrees Fahrenheit, can 3 increased to 62.2 degrees Fahrenheit, and can 4 increased to 62.6 degrees Fahrenheit. This corresponds to an overall temperature change of 10.9 degrees Fahrenheit, 11.1 degrees Fahrenheit, 9.2 degrees Fahrenheit, and 9.6 degrees Fahrenheit for cans 1, 2, 3, and 4 respectively. How does this relate to mass and heat transfer? We discussed in Lecture 3, Steady State Conduction, which corresponds to Chapter 15.5 to 6, about the critical thickness of insulation and the question, is thicker insulation for a pipe always better, arose. If we consider heat transfer only through the insulating layer, which is what we considered through our experiment, the following equation is true. dQr over dR3 equals 0 when QR is maximized, otherwise known as when the critical thickness of insulation occurs. This corresponds to the graph on the right. This means that the answer to our question is no. The greatest thickness is not always the best insulator.
The critical radius is also used in many real-world examples. With building insulation, the critical radius allows engineers and architects to determine the necessary amount of insulation needed for a building while avoiding unnecessary high costs. Additionally, with HVAC systems, the critical radius allows engineers and designers to effectively plan a ductwork that will minimize energy loss and improve thermal performance.